Oz, relax, buddy. All right. Let's go ahead and get started. So, last time we talked kind of introducing you to various intermolecular forces that can occur in between various compounds. So, let's go ahead and just do a little warm-up exercise here. Let's see. How about we start with these three compounds. Relax, Oz. And then let's also have, how about... And so, good morning, Anne. Let's take a look at these three molecules and see if we can't figure out what forces these would experience. And for that, I'm kind of going for like ones that are interacting with themselves. So like two CH2O molecules, two formaldehydes, or two dichloromethanes, or two carbon tetrachlorides. So just between themselves. And so if we want to do that, we really have a couple of questions to ask ourselves, right? We have to wonder if the molecule is polar or not. And then we have to see, do we have hydrogen bound to, oops, obviously not hydrogen, but oxygen, fluorine, or nitrogen. Oz, come here, sweetie. Come on. Come here. You don't have to be grumpy. Come here. Okay, fine. Stay there. So these are kind of the questions we have to ask ourselves. If it is polar, we know it can then do dipole. And if there is a hydrogen bound to one of those three elements, then we can also do hydrogen bonding. But we also know, without needing to do Lewis structures, that everything here can do London dispersion forces. So just remember, everything does London dispersion forces. So that's an easy answer for you. If you're ever asked, what forces, you already know it can do London. So that's 1/3 of the work done for you, right? So let's go ahead and come up with these Lewis structures. So if you are watching this later, you may want to pause it and practice doing the Lewis structures on your own. But for us who are doing it live, we will already have these Lewis structures. No, go away. No. Oh dear. Okay, good. I can undo it. Doo-doo-doo. Okay. All these lone pairs we have to draw. But there we go. We're done. Okay. So if we're going to ask ourselves, is the molecule polar or not? Remember our criteria for polarity was looking and seeing, does our central atom have different electron domains attached to it? And so if we look at formaldehyde, the one on the left there, we can see that it has three electron domains, and indeed we have an oxygen that is not the same thing as a hydrogen. So of course, we're going to expect that oxygen to be more electronegative, right? So it's going to end up being a little bit negative, and the carbon will be a little bit positive. And so as a result, because this has a dipole in it and is overall polar, we're going to say that this can also undergo the dipole forces. And then if we're going to ask, can this thing do hydrogen bonding, we have to ask ourselves, is there a hydrogen directly bound to oxygen, nitrogen, or fluorine in this molecule? And we do not have any of that here. The oxygen is not connected with the hydrogen, so there will not be any hydrogen bonding for this molecule. It can accept hydrogen bonds from other molecules, but it cannot do it by itself. So we're just going to leave it with London and dipole forces. Alrighty, so let's go ahead and look at our dichloromethane there. We can see that, again, we're going to end up having different electron domains here. We have hydrogens and we have chlorines. We know chlorine is fairly electronegative. It's got an electronegativity of about 3. Alright, hold on. Where is Oz? Where are you? There you are. Come here. Let me just pick him up so he stops. Come here, buddy. Okay, there we go. So we can see that we have, again, polarity happening here. And if anything is polar, it can undergo the dipole-dipole interactions. So we're going to expect dichloromethane to be able to interact with itself through these dipole-dipole interactions. All right, and then the last one here, we see that all 4 electron domains on carbon are the same. They're all chlorines. And since they're all the same, it's not polar. And so we're not going to have any London forces here. Or I'm sorry, we are only going to have London forces here. No dipole interactions, because there is no polarity in this molecule. So we just leave it as London dispersion forces, and that will be our answer. Alrighty. Any questions on those 3? Alrighty, so then kind of moving on here. Yesterday, we saw that the boiling point and melting point increase as the strength of intermolecular forces increases. And we also know that hydrogen bonds were going to be our strongest ones overall. Remember, they're small and relatively highly charged because of their difference in electronegativity. And then we had the London forces at the end. However, what we do know is London forces they're very dependent on molar mass. Let me actually write out molar mass here. We saw that the bigger the thing is, the more electrons it has, the more likely that there's going to just be some uneven electron distribution there, which can create those transient dipoles to attract other molecules. And we saw that, again, more electrons means more chance for that to happen. You eventually get stronger London forces overall as a result. So you're going to see plenty of examples of this in your homework when you're going to be looking at molecules that potentially could hydrogen bond or just do dipole interactions or just do London forces. And you're going to see, you're going to be able to rank those. You're going to be able to look at their boiling points and melting points and have a look and compare based on which intermolecular forces they're able to do, kind of how they're going to behave. You're going to see which ones will have the higher boiling points or melting points, which ones have the lower ones. You'll be able to judge that based on these intermolecular forces. So that'll be part of your homework there. So with that in mind, let's go ahead and talk about other IMF dependent properties. Oops. And one of them that we'll talk about is something called surface tension. And so if you have ever seen kind of, those water bugs, I don't know if I'm going to try and draw it. I guess they have 6 legs, don't they? Where they can just... Okay, this is going to be a terrible drawing, but they can walk on the water, right? With their very kind of light mass. But even so, they're denser than water, but they can still walk on it. And we're going to see that this is a property called surface tension that we're going to be able to explain with using intermolecular forces. So this bug is denser than water, but it can walk on it. So let's think about why. So if that bug were to kind of go through the water, let's take a look at what it looks like on the surface. So if you have all these water molecules kind of at the surface, just a bunch of water molecules, and if you imagine that bug's leg just kind of coming in here, here's the leg. What's going to happen is you have 2 options. You can have that leg go right through, or what you can have happen is that those water molecules will actually not break their forces, and they're going to hold together, kind of creating a place for that leg to stand on. So because those water molecules are so attracted to each other, all right, hold on. One of the dogs is like breaking into the food, I think. One sec. Small one, get away from there. All right, so now I've got 2 naughty ones that I have to hold in my lap for today. It's just getting very exciting. Here, you could say hi to them. This is the naughty one who is trying to open the food bag, and this is the Borker. So, okay. Relax, little ones. Okay, so because the H2O loves itself, that is to say they are strongly attracted to other water molecules, they will not separate. I'm going to have to move separate down to the next line. Easily. And we can also see this if you've done this kind of experiment as a kid. You can take a penny and you can drop quite a bit of water on it, and it's going to kind of form this dome of water without spilling over. Gravity tells us, hey, this water should spill over the side, right? Or if you take a glass of water and overfill it, you're going to end up with that dome shape as well on the top. And the reason, again, that this happens is the surface tension. So all the water molecules on the surface are kind of being dragged towards the middle. If we want to think about what's happening, relax, buddy. In the middle of the water, this water molecule in the middle is being attracted by all the water molecules nearby it. So this water molecule in the middle is going to be kind of happy where it is. But if we look at just the surface molecules, if we look at just the surface molecules, those surface water molecules are really only attracted side to side and down towards the rest of the water. There's nothing kind of pulling them up. So they're kind of tethered in place there. So, despite the fact that gravity says, you know what, hey, you need to be pouring over the side here, this is kind of tethered to the surface. Wow, I'm terrible at writing. By these IMFs. And so that water molecule at the surface is being pulled down and being pulled to the side, and that is enough to overcome gravity, which tells it, hey, we need to be pulling, you need to be going elsewhere. So if we just draw these like giant water molecules, this water molecule that I've drawn there is being held in all these directions. And so it's not going to fall off the edge, even though gravity says it should. And so you can try this. It's a very easy experiment. Get a penny or get really any kind of surface. Penny works well because it's kind of a nice shape and size for this. And if you just kind of slowly drop water drops onto it, you'll see that you can get this kind of really nice dome to form, where you can kind of get these water molecules to defy gravity with this surface tension. And so really what surface tension means is kind of the resistance of a surface to break off. And so if we're looking at that bug walking on the water, those water molecules are happily already chained together at the surface. And so that leg pushing down on them is not strong enough to break apart all of those bonds, those hydrogen bonds there. And so the surface tension, that surface that's not going to want to break apart, or break apart we could say as well, is going to hold, and therefore that bug is going to be able to walk on the water. You can also float a paper clip on water too. If you have some tweezers, take a cup of water, lay a paper clip on, like kind of very horizontally onto the water, you'll see that the paper clip will float too because of surface tension. It's just kind of, the water is so happy with itself, it's going to say, even though physics says you should sink, you're not going to sink because of this surface tension. All right? Oh, dogs are being extra naughty today. I wonder what it is. And so there are a class of... this is also the reason that water will form spheres if able. Because that is going to be the... okay, I'm going to put him on the couch and see if he'll relax. If you ever kind of have taken a hose and, put some pressure up and shot it into the air. Okay, hold on. Oz, relax, dude. You don't have to be naughty. Okay, relax. If you've taken a hose and shot water up into the sky, especially at higher pressures, you see it doesn't stay as a stream of water, but in fact will break apart into many spheres. And if you ever can kind of take a look at rain, rain also takes the form of spheres because of this surface tension as well. So if you look at a raindrop, we kind of have this idea of what a raindrop looks like. But really, it's a sphere that has air resistance pushing some of it backwards. So in reality, or ideally, or in vacuum, I don't know how to spell vacuum. There we go. Water would look like this when it's falling. But air resistance kind of pushes some of this water backwards. So even rain and teardrops and all that are all going to be spheres because of the surface tension. All that water wants to be as close to the middle as possible, and the best way to do that, the best geometry for that, is a sphere. And so we see that that'll be the case. So you'll see that water tends to form these kind of spheres and beads, especially if you take like wax paper too and put a drop of water on it. You'll see it will try and form as much of a sphere as possible. Or like on your windshield, you have typically hydrophobic coatings to make water not stick to it, so the water will typically form spheres. All right, just so you know, there is a class of chemicals that disrupt surface tension. Disrupt surface tension. So that means that it's going to make this water not want to form spheres, or not hold up the water bug, or not hold the paperclip up, or not stick on that penny. And we're going to see that kind of the most common one is going to be most soaps. Soaps and detergents are surfactants. They actually will break apart the surface tension of water, allowing you to make it interact with things it doesn't want to interact with. Notably like oil or wax. We're going to see that surfactants will help you to kind of make water interact with these things. Where water will normally bead up if you put it on wax paper. If you put soapy water on wax paper, you're going to see that it will actually spread out all over the paper. And so you can kind of force water to break its own surface tension, to stop loving itself as much and start loving other things as well. And so let's see. Let's see if we can... probably should have done this beforehand, but let's check YouTube real quick. Paperclip on water surfactant. Let's see if we have a nice way of doing this. So let's go ahead and swap over to YouTube real quick. We can see this in action. So let's go ahead here. So of course we're going to have to deal with 10,000 ads here. Go away. Go away, State Farm. No. Go away, random cell phone game. Okay, crazy Russian officials. Alright, so you can do this at home. So you can use tweezers instead. He looks like he's using a piece of paper or something. He's failed. You really want to get it so it lands really flat on this. Okay, so he's using tissue paper or something. That would work. And so you can see here that you end up with the paperclip floating on the water, even though it wants to it wants to sink there. Here, hold on. Let me find that one. Where did it go? Okay. Let's look at this kind of in more detail. So you can see actually on this that water, normally you can see whatever writing that is at the bottom, but you can actually see a little distortion here around the paperclip as that water is struggling to maintain its surface tension. It's trying to stick together with other water molecules, just kind of dragging it downwards a little bit, which distorts that image down there. And so if you look around it, you see that the water is kind of puckered a little bit around that paperclip. And so you're going to see that for that reason, the surface tension there is going to be important. Let's see what this guy's doing now. Okay, he's got some soap in there. And notice immediately, as soon as he put the soap in, what happens? Paperclip sinks. So just one more time. Paperclip sinks. And actually, I think right there you can really also see the distortions of the water really easily there as well. And so in goes the soap, down goes the paperclip. Interestingly, you can try this with black pepper too. Works really well. If you put black pepper on to some water, it'll float there. Put a drop of soap in, you'll see all that pepper is going to fly off to the sides just as a result. So pretty cool stuff you can do there. So these will disrupt it. These are very useful on things like windshields in your car because you don't want water to bead up. Because if water beads up, you end up not being able to see through it. But if you can make the water flat and kind of fly off the windshield, surfactants are going to help do that. And so a lot of your windows and stuff will be treated with surfactants to help water not bead up so you can see through it more easily. And of course, we're going to see that these detergents will mess with that surface tension. It's also important in your body. Your lungs will constantly have to release a surfactant so that they can maintain their nice alveoli shape. But that's biology. You can learn about that when you take physio. So, but important stuff here. Surfactants typically have they have polar bits and non-polar bits. And so you might have something where it's like a long carbon chain and then a polar bit at the end. So something like this, where you would end up having a polar head group and a non-polar tail. This is, again, something you've probably heard about with phospholipids. Those can definitely act as surfactants if you have them in the right concentrations. If you have, just depending on the properties of these, they might form bilayers instead of monolayers, and they would act differently. But, your cell membranes are made of similar molecules to these. Where you have polar parts and non-polar parts that can interact differently with different things. And so that's how the surface or the surfactants are going to work there. Alrighty. Any questions on that sort of thing? Anything about surfactants or surface tension? Alrighty, again, the main point here is that the higher your intermolecular forces, the higher your surface tension is going to be. And so you're expecting things that have strong intermolecular forces to have strong surface tension. Okay. Another one we have is viscosity, which is the resistance to flow. As a liquid. This is it can work for gases too, but typically we talk about liquids with regards to viscosity. And just to kind of put this in context, something like honey is more viscous than water. If you try and pour honey, you can, completely upend the honey jar, and it's going to very, very slowly come out. It flows very slowly because there's a high viscosity. It resists moving. But water, if you were to take a cup of water and turn it upside down, the water is just going to come straight out. And so we're going to see that strong intermolecular forces will lead to high viscosity. And another example that we might talk about, honey, by the way, is filled with glucose and fructose, which have a lot of hydrogen bonding units that can really nicely hydrogen bond with water. And so that's the reason that that honey will have more intermolecular forces. But another common example would be something like gasoline versus something like crude oil or even engine oil. If you've ever poured engine oil or even something like olive oil, it flows more slowly, right? Gasoline is going to be something around C7H16 or so, depending on heptanes and octanes in there. Oils tend to be more like, C20, H40 or something like that. And so you can see here that the bigger molecule would have stronger London dispersion forces. And so it's going to pour more slowly. Gasoline flows very quickly. We can pump it really, really quickly at the gas station. But oil pours pretty slowly. If we were to just compare, gasoline would just completely come straight out. Oil, you have to hold that can over your car, for a while to let all the oil go through. It takes a long time, especially to get those last little bits. And again, so we're going to see that your stronger intermolecular forces will end up giving you something that has more viscosity overall. All right. Another property would be adhesion. If you look at a water glass closely, you'll see that water is attracted to glass through dipole and ion interactions. We're going to see. You don't need to know that, but this is a property as well, where we're going to see that water will actually climb up against gravity a little bit to the side of the glass because it's attracted to it. So this is a type of interaction between the silicon and oxygen. So glass at its surface has negative oxygens. The positive bits from water can interact with those negative charges on those oxygens, and the water will climb up the glass a little bit. You can also have capillary action here, where water can be pulled up, within a glass tube by itself, because it's attracted to it. You can go against gravity. And so we can see that the water will go against gravity because of attractive forces. So adhesion is going to be two things attracted to each other that causes them to kind of stick together. And so when we use glue and other adhesives like that, notice, we're trying to get things to stick together as well. So the water is going to be kind of attracted to the glass, it's going to stick onto the sides, it's going to go up a little bit. The opposite of this is called cohesion, where this is actually what you see if you were to take liquid mercury. You would see that mercury hates the glass and will repel itself. The cohesion is meaning it loves itself more. It's going to stick with itself more than it would stick with something else. So this would be liquid mercury. So if you ever are in a hospital and you see those kind of old blood pressure monitors, they have liquid mercury inside. It's a silvery liquid. And you'll see that if you were to look closely in those glass tubes, you're going to see that kind of shape where the mercury is avoiding the glass. But if you look in with water in the same type of thing, or even look on a water glass, you'll see that water will creep up the sides rather than be repelled from it. So it's all about just how these things are interacting. So things that like each other will adhere to each other. Things that don't will have cohesive properties. Instead, they will prefer themselves to interacting with others. You could think of cohesion as kind of introverted molecules. They just kind of want to be by themselves, and that's great. And then on the other side, you have the adhesive ones, which are more kind of the extroverts. They want to hang out with the other molecules. So we're going to see those are two other properties that we can have with regards to intermolecular forces. So, any questions on that stuff? Alrighty. Well, that's kind of is. Or did we talk about vapor pressure yet? No, I don't think we did. Okay. Our last one here, vapor pressure. So, if we have a sealed container, and we put some water in it, we know, of course, we have liquid water down here, lots of it. But we know that there will be some molecules that will have evaporated, and they're just going to be gaseous water up there. We know that water evaporates even at room temperature. Yesterday, again, we kind of looked at those graphs, those distributions. We see that even at kind of low temperatures, we still have some molecules that have enough energy to boil or something, even a little bit. And so we will always have gas particles above a liquid. And so we're going to see that the stronger intermolecular forces will lead to lower vapor pressure. Because if we want to think about water molecules turning into a gas, they have to get away from all the other water molecules. So again, you have to break all those happy interactions. And so if you have strong intermolecular forces, you're going to have a lower vapor pressure. If you have something like, let's say, how about acetone? We're going to have a lot more acetone molecules. Acetone, by the way, can do dipole forces but no hydrogen bonds, so it has weaker intermolecular forces than water. And so acetone has a higher vapor pressure than water, because acetone has weaker intermolecular forces. Oh, I was hoping I could put that there. We might describe acetone as volatile. Volatile means it has a high vapor pressure. Another way to say that is it boils easily. I don't know if any of you have ever felt acetone. You can use it as a nail polish remover. It's also used in a number of industrial things. So you might use it as a cleaning agent or a solvent. If you get acetone on yourself, it'll feel very cold and it'll boil off your skin very, very quickly compared to water. And so it feels cold because it's extracting the energy from your skin as it boils away. That's something we'll talk about next time. But we're going to see the same thing with gasoline. These things evaporate very quickly because they are volatile. They have high vapor pressure. They go away very quickly because they have weak intermolecular forces. So if you spill gasoline on the road, which hopefully you shouldn't do, you'll see that it would evaporate very quickly. But if you were to spill oil instead, it doesn't evaporate, right? It evaporates very, very, very slowly, so much so that it's pretty much not even visible. And so we're going to say that the gasoline would be volatile, but the oil is not. The oil would be non-volatile. And so we're going to see that something that is volatile will have a high vapor pressure, meaning it boils easily. And we're going to see that vapor pressure is inversely related to IMF strength. So low IMFs means high vapor pressure. High vapor pressure means you boil easily. That means you also boil at a lower temperature. So it's the same idea that we've learned before. We'll talk about vapor pressure a little bit more next time when we talk about kind of phase changes in between solid, liquid, and gases. So we'll look at that in a little bit later. But suffice it to say, for right now, stronger IMFs means low vapor pressure. So I'll write that in purple. Strong IMF, low vapor pressure. It also typically means high surface tension. And it also typically means high boiling point, melting point, relatively speaking, of course. And then what else do we talk about? High viscosity. So this is kind of the summary of what we've talked about today. Is that strong intermolecular forces lead to these 4 properties, or 5 if you include melting point as a separate one. And so it's kind of a correlation we can make. So just being able to judge the intermolecular forces of a particular substance, we can learn or predict quite a bit about its properties. And so that's kind of all I wanted to cover today. I was expecting a few more questions, but that's okay. Maybe this is all making sense. Conceptual ones are nicer for some students who don't like math. This stuff is so far no math, right? So it's just all conceptual. I guess we can talk about your exam for a sec. So your exam again will be Monday. So you'll take it at some point on Monday. You'll be able to see the time limit on Canvas. It'll be about the same number of questions, roughly divided between the topics that we've had so far. Multiple choice, same as as last time. There's not going to be a stream on Monday for us. Again, if you do want to do a review tomorrow, you guys have to put questions up for me to go over. Otherwise, we'll skip the review. You'll be able to see your answers and the correct answers on Tuesday once I unlock those. But you will see your score right away, of course, since it is automatically graded on Canvas. Of course, it's going to be open book, open note, whatever you want to use. But just keep in mind, the more notes you have, the longer it will take you to go through those. And so just keep that in mind as well as you're studying for this. Your homework is due Saturday. Don't forget, due Saturday, so that on Sunday you can look at the homework answer key, which I very strongly suggest you do because there's a lot of topics covered there, and you want to make sure that you're fully understanding everything. And of course, you can throw written questions in Discord as well over the weekend. I'm always happy to go over those. So, yep, that's what we're looking at. So 3B to 5B. So I guess that's four chapters. So 3B, 4, 5A, 5B. again, today's stuff, of course, would not be on it. This is chapter 6. Um, so again, we're kind of looking at a roughly even divide among those chapters. So there's not one you should study more than the others, but yeah. Let's see. Anything else we should go over with this? There are practice exams, of course, on Canvas. It may be helpful to look at some of the ones from like exam 1 because they may still have some stuff on like mass percent. So if you want to practice those, I think those might be on exam 1 on the practice exam. So it may be helpful to look at that as well. But yeah, that's pretty much it. So next time we'll talk about solids, liquids, and gases and how to go between those and all that sort of thing. I guess that'll be Tuesday next week. So I guess with that, maybe I'll see you tomorrow if you want to do a review. If not, have a glorious weekend. Enjoy your studying. Good luck on your exam on Monday. And yeah, study well. Let me know if you have questions. And take care then. See you guys later.